Thank you all for coming. My name is Paul Beal. Judah Levine and I are the hosts of these events throughout the year. So before I introduce the speaker today, the next talk is February 28th, same time here in this location, 2:30 in the afternoon. And it will be Colin West. He's going to be talking about the history and current the evolution of Schrodinger's famous equation. It's the 100th anniversary of Schrodinger's paper this year. So our speaker today earned his PhD at the Max Planck Institute for Quantum Optics and the Technical University of Munich. He joined the physics faculty in 2010 after research stints at Berkeley and the Max Born Institute in Berlin and at the faculty at the University of Washington. His current research, I'm always amazed when I tell this little bit of a story. He's able to measure electron behavior at its natural length and time scales in the nanometer range length scales and femtosecond range time scales. So he works on studying the way the electrons behave in actual materials in their natural environment. Today he's going to be talking about quantum mineralogy. Markus Raschke.
All right, thanks, Paul. I don't recognize myself in this praise. So yeah, thanks everyone for coming. The weather is nice outside, so nobody went out digging for minerals and measuring their quantum properties. So maybe I first give you the introduction before you head out and go collect minerals and looking for their quantum properties. So yeah, so I'll talk a bit about, in fact, a field where the title or the term is not well established. And it's in part a convergence of personal interest in field collecting in mineralogy and then also in the research we do on what actually makes a quantum material, which is the complex interaction between the building blocks and the material, primarily the interaction of the electrons. And then the electron has a spin, which gives rise to a magnetic moment, and we'll talk about that. And then also how it's coupled to the atomic motion, which is, again, interacting with these electron degrees of freedom. And so what I'll tell you is, in fact, another convergent story where in earth sciences, where minerals are dug out of the ground and then their structure is studied and the properties measured, how that actually inspired itself the field of condensed matter physics, in particular with structural motifs which host quantum properties. And then conversely, as we in condensed matter physics can synthesize these materials, these synthetic pathways re-inform actually earth sciences to help understand how rock forms, how ore forming processes gives rise to mineral deposits. And so this is sort of a bit story of these multiple facets. And it ties into fundamental aspects of quantum mechanics. And as Paul mentioned, there is different decades we celebrate actually different transformative events in the history of quantum mechanics. So a key event was in 1905, where seminal papers from Einstein laid the foundation on the quantized nature of the photon or of matter in general. And then the development of quantum mechanics hit sort of a snag in the early form of how the idea was that electrons run around the nucleus in sort of orbits. And this made it actually very difficult to describe the fundamentals of light-matter interaction. And then Werner Heisenberg then had sort of a breakthrough moment where he was actually on an island in the North Sea in Helgoland, where he went because of his hay fever and looked for a reprieve. And then he derived actually by recognizing or thinking of that we cannot observe actually these electron orbits, but recognizing that what we can measure are actually spectral line positions. And then he reformulated this light-matter interaction in a very abstract mathematical form which didn't have what looked like this pictorial idea that we have these orbits, but was tying it then to, even though through more complex mathematics, to these observable of these spectral lines which hydrogen emits. And then he came with this very peculiar mathematical formula, which is even dangerous to actually show to school students, because then you think that everything you learned in mathematics is wrong. Because if you actually multiply, so you have this formula where P times Q minus Q times P. So if you multiply 1 times 2 minus 2 times 1 is, last time you checked, right? That was so. But then and it's not in this original paper, but Heisenberg tells you that this is only sometimes so. But sometimes it's not, and sometimes it's h over 2 pi I, which doesn't matter what that is for the purpose of this talk, but it is non-zero. And what this shows, and this is a more complex equation, this is a simplified form to write it in this so-called commutator relationship. But what it does show is that you cannot measure certain properties as you can do in classical mechanics with exact and high precise information. For example, the position of a particle and the momentum. You can, in classical mechanics, you can just say the particle is moving, and you can have a position, and you can determine its momentum, or the same with energy and time. This says that these properties you cannot measure. If you know the position accurately, you cannot know the momentum, and vice versa. And the relationship and this uncertainty, and from this is actually where this uncertainty principle was derived, that you can only know one or the other, or a trade-off between the two with a certain precision, given by this uncertainty relationship, which goes back to Heisenberg. So this was then formulated in 100 years ago, and that revolutionized quantum mechanics and made problems solvable, especially like matter interaction. And the reason why I'm showing this actually is because we will talk about magnetism. And one of the properties of magnetism is the spin of the electron, and the direction of the spin is which equally follows this commutator relationship and cannot be measured with certainty if you know a spin up or down versus a left and right spin orientation. Okay, so this is sort of the plug-in and the connection that these quantum properties of materials are tying, in fact, to all of these phenomena of electrons, their spin and their motion, and then this delocalization of an electron wave function, which is this consequence that we describe them as waves. And so maybe just a brief word about who I am. So I am not a mineralogist. I'm actually also not a qualified condensed matter physicist. I never actually know what I am, but what we think we are reasonably good at is actually to do microscopy with very high spatial resolution, where we take scanning probe tips and localize an optical field. But we do study molecular and quantum materials this way. As Paul mentioned, we probe the electron dynamics and lattice dynamics in these materials. What I do as a pastime is that I roam around in the mountains and collect minerals. So this is my mental escape from that part, or this is a mental escape from that. And this has also led to some research effort, one of which is actually very prominent and of high relevance in the United States now, is to develop a autonomous source of rare earth minerals and other critical elements. And so we have discussions on this. Connected, this is my personal uncertainty relationship, that if I do one or the other, and then the students can find me when I do one or the other. Okay. So let me tell you now a little bit on the history of mineralogy and how it has evolved as a discipline, and actually how significant it was as a discipline. So as people found rocks and had crystals with nice crystal shape, they were historically described in a very qualitative way. People measured the crystal angles and then tried to derive something about the internal structure and how the atoms are arranged in these materials. And so mineralogy was then establishing all the principles actually of crystal structure, and everything derived of the periodic arrangement of atoms in these crystals was sort of a key factor. Now, on the other side, where we are today, is that we develop quantum materials. Yeah? And a lot of these materials have actually direct technological importance. So we use magnetic materials, or we use metal insulator transitions. We use change in strain and in optical response for sensing, in computing applications, the entire field of semiconductors, then data storage, all the energy conversion. The solar cell is a quintessential quantum mechanical device, and also catalysts. And what has really transformed this field is that mineralogy was initially a purely observational science, and then purely descriptive. And this has changed now to a synthetic discipline where we are making materials, sometimes very well informed by theory and truly by design, and can actually predict to a certain extent the material properties already beforehand. And this is one of the connections actually between earth science and physics, which often hasn't been fully appreciated. So a famous example, which you're all familiar with, is actually this material. This is magnetite. Magnetite is in some sense the oldest quantum material recognized to be such, and this is that you have these magnetic properties of this stuff. So you can find magnetite. It's the iron ore which is dug in millions of tons, and it's magnetic. Yeah, and the magnetism of magnetite was recognized very early. So there are descriptions of it where it was used as a compass. So it's magnetized in part naturally, and has a north and a south pole. And the ancient Greek already put this magnetite on a wooden plate and had that float in water, and it would orient and function as a compass. Yeah, so this was recognized, and then over hundreds of years, there was philosophers who always tried to explain this phenomenon, and it has no classical description. So this is a purely quantum mechanical effect. And the beauty of it is in some way that if you can hold quantum mechanics in your hand, okay? If you actually take a piece of magnetite and wonder about it. And there are different places actually in Boulder County where you can actually collect some that just outcrops up by Netherland, for example. And it's a fun for kids to walk around as a magnet and pick it up, right? It's just a dense, heavy rock. So, but that's sort of the fascinating effect. And then what is further fascinating, that the exact details of the magnetic origin of magnetite are actually fairly complex. And there is still ongoing research about deciphering further details about the exact origin. And this is because the physics of spins and spin behavior is, in fact, fairly complicated, even though you wouldn't think at first glance. So you have this electron, which is like a little magnet, and it has actually only two possible spin directions. It's either spin up or it's spin down. It has a magnetic moment, which is 1/2. This is a feature of what is called a fermion, but that's not even a critical piece in this puzzle. And so you wouldn't think that something very complicated could arise if you actually have just two bar magnets and they can orient only in two possible quantized direction. But I'll show you that there is a complexity, especially in magnetite, actually. And so how are these spin oriented and arranged? And so in magnetite, this is this iron oxide, but what matters here is that we have a mixed valence oxide. So this means that we have iron in this formula, and the iron has two different oxidation stages. So in one case, it has lost, compared to the neutral atom, 2 electrons. So this is this iron 2 plus. And in addition, in this lattice, there are 2 more of these iron atoms which have lost 3 electrons. So this makes them 3 plus. And they are sitting on 2 different so-called sublattices. Yeah, so to walk you a little bit through this structure, this is a cubic spinel structure for the experts here. And there is a tetrahedral coordination of these 3 plus cations. And then on this octahedral coordination, this is where you alternatingly have an iron 2 plus and an iron 3 plus ion. And so you have these 2 sublattices. One is in this tetrahedral and one is in this octahedral coordination. And what I can already tell you, if you were to go home and imagine this evening let me think about some creative structure which should show exotic quantum phenomena, you often have interesting properties when you have such 2 sublattices and you have this mixed valence occupation of these cations. Yeah? And I should add actually that this wouldn't happen. So in what way is iron actually special? And of course, I'll start with this because everybody knows what iron is. And so you can search it over on the periodic table. And on the periodic table, you have what's called these transition metals here. Yeah? So these are all the metals which you're familiar with. So there is copper, and there is silver, and there is gold. Yeah? And so all of them have a particular electronic configuration, which all makes them favorable for interesting quantum properties. So this is a lot of these transition metals in the form of an oxide. This is one of the favorite properties. Okay, so we have these 2 types of coordinations of these mixed valence iron. And then let's think about how can we organize spin. So I showed you the 2 electrons. They can point up or down with respect to the crystallographic direction. And here are different ways of doing this. You can have this electron spin all parallel. And this is called ferromagnetism. In fact, this rare earth magnet, which I was using to lift this magnetite, that is a rare earth magnet, and that is, in fact, a ferromagnet. So then you can think about another arrangement, and this is where you put the spin into an anti-parallel organization. This also sounds like this is a stable ground state in a well-defined arrangement. So one goes up, then you put the other one down and up. And you see that on a rectangular or on a square lattice, you can easily do this. And then this has no magnetic moment, no macroscopic magnetic moment. You would not be able to lift that up as a magnet from outside. So this is where the magnetism internally cancels. And then there is this type. And this is now when these magnetic moments, so depending on the number of electrons on an atom, then these 1/2 can add up to multiple of that. So if you have one ion which has several of these spin states in one direction, but then the other one has only a fewer or less, then they can also organize themselves in this anti-parallel arrangement, which would then give rise to a weak, what looks like ferromagnetism. So you have an external magnetic moment, but it would be partially canceled by this. So now there comes the question and some funny keywords here of what happens now in this magnetite, that it is actually magnetic. And there's a lot going on here. So there's an indirect exchange actually between these 2 sites. And this is what is called an exchange interaction. And then there is another mechanism which is actually called a double exchange. So this indirect interaction is a super exchange, and there's a double exchange. This is a terminology for describing the details of these interactions. So if you now look at, say, these two ions here in this one, so now we're zooming in into this octahedral side of one of the ions, and then the tetrahedral coordination where we have the 3+ cation, so this sits on that side. And so through this interaction with this oxygen, these two iron interact, or their spin interact through this oxygen ion. This is called the superexchange interaction. And in this case, this is the interaction when there is an iron 3+ sitting on this side. This is this scenario here. So we have this 3+ on the octahedral side and a 3+ on the tetrahedral side. And then they have the same number of spin of these electrons. And they can arrange in an antiferromagnetic order. And this is why those two completely cancel. And so what is left then is actually the iron 2+ on the octahedral side, which are actually occupied with a 2+ cation. And they can interact with each other. This is then this so-called double exchange, which goes through this oxygen bridge. And so these ions interact, and they can then align parallel. And this is why magnetite is then ferromagnetic, where these iron 2+ then give rise to this net magnetic moment, and therefore this ferromagnetic order. So this is now what the Greek didn't know, but what we know now, that this is sort of the mechanism primarily giving rise to this magnetic order. And again, the fascinating effect is really that this is truly what you can find on the street. So then there was an interesting experiment done, which is in some ways surprisingly late. And if I had had more time this morning, I could have actually just demonstrated this to you. We could use a voltmeter and apply a voltage, or measure a current, apply a voltage across this crystal, and we measure a current. And we would actually see that magnetite is actually a conductor, not the best, not as good as iron, because of these oxygen atoms through which you have to then hop these electrons, but it is conductive. And in 1940, a Dutch physicist actually cooled this crystal and recognized that there is a phase transition. And this conducting behavior changes as you start to cool. So here we are at room temperature, 300 Kelvin. And so you're cooling down to about 90, or what is this actually, 120 Kelvin. This is below above liquid nitrogen temperature. So, and then you see a jump in the resistance. So this means that you will turn from a metallic behavior into an insulating behavior. This is a logarithmic scale, so you get a first order transition where the conductivity abruptly increases by 2 orders of magnitude. Such a phase transition is what you know from water freezing to ice or back melting to water. This is similar, a phase transition between a solid and a liquid phase, and here it is between a conducting metallic phase and the insulating phase. And then there is a continuous increase again as you keep cooling where the resistance increases. So this was discovered in 1940, and there was really no good explanation for this. This was the first quantum phase transition in a material discovered. It was that late. The experiment could have done decades earlier. And it set off the field in quantum condensed matter physics, where it was recognized that compared to all these simple previous phases of liquid and solid and gas, now apparently we can switch a material from a metal to an insulator and back. And this mechanism now is more complex, actually, than this magnetic behavior. because now we need to couple these iron cations in a particular way so that the electronic orbitals overlap and to form a metallic phase, but then also we want to decrease this overlap so that the electrons stay localized. Yeah? And this is part of this picture about conductivity, where we have electrons localized and they don't leave their site, and where we have electrons which would leave a site and then can percolate through the material. And so above 120 Kelvin, so at room temperature, and this is this crystal, I asked it this morning, it confirmed that I'm in a cubic phase. You can actually see the cubic structure. If you want to come up later, you see the symmetric crystal faces. Yeah, so this is cubic. And so what happens at low temperature is that the crystal structure changes. So it's no longer cubic. We will have a change in these crystal angles. And so this unit cell distorts. And then this distortion actually then leads to a different interaction between these iron cations. And this was only worked out actually less than 6-7 years ago, where it was recognized that now these iron cations form what's called these trimerons. So there are these 3 2 plus and a 3 plus and a 2 plus, or the other way actually, this is 3 plus 2 plus 3 plus, forming this so-called trimeron, and this locks the electrons in place, and it becomes an insulator. And this in general has actually been a very important and foundational principle, that we have apparently a coupling of the lattice structure, so the position of the atoms, and so this is this lattice, with the electrons, and the electrons are responsible for the conductivity. And then further, and this is not shown here, that of course also this spin order is temperature dependent, and so we have then also a coupling to these spin degrees of freedom. And this is the foundational principle of what's called correlated quantum materials, which is this interaction between the spin and the electron and the lattice properties. And this determines then in complicated ways many of these quantum phenomena, including superconductivity. We'll talk about this a little later, and many other then coupled electron lattice and magnetic phenomena. Yeah. Yes. Can you say this again? At 112 Kelvin is where this phase transition occurs. Oh, how you would change the temperature? So you could just simply take this crystal and dip it into a cryostat, or in actually liquid helium or liquid nitrogen, and then just watch it cool. Yeah, or you can actually couple it with a heater to a cryostat, and then you would balance between the cooling power and the heating power of an electric heater, and then can actually also stabilize a certain temperature. Yeah, so it's not that different from using your kitchen oven and put a pot on it, right? You have a dial and you set it to the water to a certain temperature, where you balance the amount of heat you put in the pot and the radiant cooling from the pot, right? So this is just the only difference is that you need a cold bath, right, where you attach the crystal to. I'm going forward here. Okay. So what was the question again? This picture. So yeah, so above 120 Kelvin, it is cubic. and then below 120 Kelvin, it is monoclinic. So the crystal structure tilts, the unit cell angle changes between these three crystallographic axes. So exactly at 1 quantum Kelvin, you have quantum fluctuations. This is also a regime which is very poorly understood, actually, yeah, where the system fluctuates, yeah, between these two phases. Yeah. And how sharp this transition is. So ideally for a first order phase transition, this is actually exactly a sharp transition. So even a very small, infinitely small increase in temperature would put it on one side, and an infinitely small change to the other side would switch it in the other direction. That is the ideal case for such a quantum phase transition. And this is, in fact, a very active research field about phase transitions in matter, because this isn't all that trivial. There is sort of some pre-ordering in the material, which, so basically when you start to approach it, would you see anything in the material already happening, knowing that, oh, I'm close to something changing? Yeah. So this is also, in fact, in ice nucleation, an open question, yeah, how these processes would happen. Yeah. Yeah. Okay. Thank you. I get the point. Yeah. Okay. So as I mentioned, this coupling between these different, what we call in solid state physics, degrees of freedom of the electrons, so the charges, the spin, the arrangement of the atoms in the form of a crystal lattice, but then also the orientation of these electronic orbitals also play a role. And so the electrons sitting in these orbitals, and this is why also this tilt in the lattice allows then these ions to orient and the orbitals to overlap in a particular way to form these superposition state, these so-called trimerons and these iron. So just to mention this briefly, this is now really for the few who may really care about this in grander detail. There are mathematical models which allow to describe these phenomena mostly effectively. Many of the details are not well understood. And there is a famous model which is called the Hubbard model, which is a great simplification, actually, of what is really happening. But it has been successful of describing some of these phenomena, and it has to do then with the two key parameters. One is actually this electron interaction. The electrons, they would repel each other. Yeah? This is because of the Coulomb interaction. Yeah? So where like charges try to stay away from each other, so then they would arrange on a lattice and they would stay bound. And in this case, you would have an insulator. But now if there is a so-called hopping parameter, yeah, this is this T, this describes sort of a desire of the electron to jump, and this is often temperature dependent, so you can think of this electron gets promoted through thermal excitation to jump a lattice site. So if this hopping interaction is larger than this Coulomb interaction, then the electrons can flow through the lattice, and then you have a metallic state. And what is unique about what I mentioned, these transition metals, famous examples were manganese and the iron and ruthenium. These are particularly prevalent, having different oxidation stages, and then everything is in these orbitals and how these orbitals are arranged. But also what's special about these orbitals is that they have sort of an intermediate size compared to the other elements, so in particular the alkali, yeah, or then the semiconductor. Yeah, these are generally larger orbitals on this side, so this makes them more insulators, and these are very good metals, yeah, because this is where these orbitals are large and the electrons like to overlap. But these d electrons are special, that they're sort of an intermediate size where the electron can't decide whether today I want to be localized and the other day I want to be delocalized, yeah, and then I'm an insulator or a metal. Okay, so this is sort of a little technical excursion, but what has shaped the entire discipline is sort of a little bit this diagram that we have elementary building blocks in these material and these elementary degrees of freedom. And then through the magic of quantum mechanics, yeah, you're solving essentially, you put in the lattice positions and the number of electrons, And then you can try to solve. In practice, this is, as of today, only possible in limited cases where you can get exact solution. But it's a quantum mechanical process which gives rise to sort of a low level of particular quantum phenomena. Yeah? So these are sort of keywords, some of which you may have heard, like superconductivity, this metallic and magnetic behavior. And then there are other keywords which condensed matter physicists care a lot about. And I added actually one thing because this is what I'll talk about also to you later. And then on a next level, there's actually forms with materials put in the appropriate configuration, then actually a basis for technology. So superconductivity is the idea that we have low resistance or no resistance conduction. We can use a lot of the magnetic properties in combination with other ferroic order, like the forming ferroelectric behavior for data storage. Yeah? And then you can use some of these superconducting behaviors also for magnetic sensors. And this is actually where there is sort of a basis for technology. However, one of the big challenges is actually that these are very fragile states. So they often occur at low temperature. They need very pure materials, so where defects and disorder can actually disrupt a lot of these phases. And this is why you can call them actually very fragile. And so I'll show you now one of these very exotic phases. And this ties it actually back again to the naturally occurring materials where nature has actually inspired the discovery of a particular unusual property, and this is a spin liquid. So what I showed you in magnetite was a spin sits on a cubic lattice. If you put one spin up, you can either have a parallel one or an anti-parallel on an ordered lattice, and you know how they should arrange. But you can think of actually a crystal structure which doesn't allow you a well-defined spin order. And so there's this picture that you have spin which is floating around, and they don't know which way they should organize, even at low temperature, even at ideal 0 Kelvin. And this is actually what's called then a spin liquid. So if you can think again about a square lattice, you know exactly how the spin needs to organize. So this goes up, this goes down, and then if you have these two, then if I go this the opposite direction, then I can put this up. And so you form a stable ground state of the material. If you would actually put little bar magnets on a square lattice, this is actually how it would organize. Now try this on a triangular lattice. If you try it on a triangular lattice, you will be confused. You can put this down and this one up. And then what do you do with this one? If you put it parallel to make it parallel to this, then it's anti-parallel to this. But then if you make it the other direction, then it's anti-parallel to this. So this is what's called a frustrated situation. Yeah? So there is no clear defined ground state for this. Yeah? Here there's just no other option to point this up to make it, then these arrows point towards each other, these point in the opposite direction. So a triangular lattice leads to what's so-called frustrated magnetism. And so now you can think of a number of different lattice configurations. There's this triagonal lattice, which I just said. Then you don't know what to do with this. And then there is sort of this type of lattice, which is a Kagome lattice. And for those who are quilting, they like these kind of patterns. So these are nice quilt patterns. So a Kagome lattice. You've seen this in different artistic renditions. Or a honeycomb lattice, right? And so what these gray shaded areas, they sort of indicate what kind of spin interactions you would have. So if there were a spin sitting here, then what we would interact with. And then there was a question about would we be able to have such a material? So this was theoretically hypothesized. And then there was the search for, is there actually a material which would show this? And this is where actually the mineralogy came to the rescue, because as more and more different types of minerals were discovered, and then more and more different structures were actually recognized in different structural motifs, which you can then populate with atoms and corresponding oxidation states and electrons. And so this is actually where I needed a shout out to Liz, a graduate student in my group, who actually helped put this part together. This is actually going to be part of her comprehensive exam topic. So in this mineral, which is actually a very common mineral, has been discovered in 1852 in Spain. It's a very simple sulfate hydroxide with these 3 iron 3+ cations. You already know about iron cations. And this actually forms Kagome lattice. And this is why this was more closely looked at. Liz is teaching me that there was a problem with this material, though. So it forms a Kagome lattice of these iron cations, which sit on these lattice sites. But because of this very strong iron 3+ spin state on these materials, the spins don't stay in this plane. There is a long-range interaction which gives rise to sort of an out-of-plane tilt. And this actually then freezes the spin, and this is why this is actually then turned out to be a spin glass. So this was not quite the solution to the problem. So the search then actually continued. And another mineral was looked at. And this is Herbert Smithite. This is oftentimes minerals are named after not the person who describes it or who discovers it, but mostly honorary by some friends or family member. I'm actually very much against putting too many humans into the science. So they could be named after crystal structure or the properties. But this mineral now is looking at copper iron. So it's a hydroxychloride, and it has these 3 copper ions per unit cell, and they are also arranged on this hexagonal pattern. There's another interesting side aspect to this. This is actually, there is different types of these minerals discovered in South America and these copper deposits in Chile and the Atacama Desert. And so there are derivatives of these minerals which are named after Atacama, so Atacamite. And so here's this Kagome lattice pattern again. Here are the copper cations. And on this material, because the copper has a weaker spin, so it's only spin 1/2, then the spin orientation stays completely in this lattice plane. And surprisingly, indeed, they were actually discovering this spin liquid behavior on this material. So there is a theory to it, which again ties to Mr. Heisenberg in the so-called spin Hamiltonian, how you need to look at different spin on neighboring sites. So, and then there is a coupling strength between them. So you look at and write this lattice, and you populate this with the copper ions. You have these individual spins on these different sites. So I and J would just label these in a coordinate system, and then you sum over these and adding these interaction. If it were so easy, right, then yes. So if only it were so easy, yeah, but the exact values are not trivially known. But then you can determine a phase diagram as a function of these different coupling strengths, and then you can actually show that this forms a Kagome quantum spin liquid. And this was not actually in this natural mineral, but they were synthetic compound, because if you do this in the natural mineral, there are often defects because of the fragility of these quantum phases. Often, as in natural minerals, you don't have this pure end-member composition. Sometimes you do, but sometimes you want to resynthesize this material in the lab. And this graph is the temperature dependent of what's called the magnetic susceptibility. And in contrast to what I showed you earlier, say in magnetite, where there's a sharp phase transition and a change, here there's just a continuous change of that value. And this shows that there is no stable common ground state formed. And this is why this is what's called a degenerate ground state, where these spin are constantly fluctuating around. And actually, if you build this as a model with bar magnets, you can actually see that you can flip one, and then all the others are randomly reorienting, and then you flip another one, and then there is no predictive behavior how these spin would orient in these materials. Okay. So there's a wide range. I just showed this for a little pretty aesthetic interruption here. There's a lot of minerals which, especially in recent years, have been revisited and looked at, which have been known in part for a long time. And then with a closer inspection on this lattice structure, trying to determine if they would inspire some new quantum mechanical behavior and potentially quantum properties. This is a very unusual mineral. This ties actually to a research project we have in China in the mountains of Sichuan province. Is muscistanite. This is actually the green coating. The core is a different tin mineral. And it has these hydroxyl ions. And these hydroxyl ions also, they don't know what they should do. If you look at the crystal structure, you either need to orient them just like the spin orientation. If you want to arrange them properly, one would point this way, you want to point the other one down, and then this forms sort of on a square lattice, a circle like this. But then this is completely degenerate with this form, so you can turn it around and have them in the other direction. Yeah? And this, again, forms a superposition state where the material doesn't quite know what it should do. But again, a pattern to look for is where people look for is different cations in different sublattices of different oxidation states, again, as an indicator. Probably can find this. So in this case, this would be also a potential candidate, which has recently been studied as a potential unusual spin material, is the superposition state. Okay, let's talk about another property, one you've heard of in the street, which is superconductivity. So are there naturally occurring superconductors? So I encourage you to go for search. I give you the hint where to find them. So what characterizes superconductivity is a phase transition where the electrical resistance now drops to 0. In the magnetite, this wasn't 0. There's still a finite conductivity. It's a metal. So it has a good conductance, so a low resistance, but not 0. So a superconductor, the conductivity drops to 0. And it has another effect, which is called the Meissner effect. And this is where if you put a superconductor in a magnetic field, the magnetic field will not go through the superconductor. So the superconductor expels the magnetic field, and you have a magnetization-free space in that superconductor. And the reason why I mention this, because you will hear about Mr. Meissner in a minute again. So there has been a huge search for superconductivity for ever higher transition temperatures. So for the longest time, in many of the conventional superconductors, since the first discovery by Kamerlingh Onnes in 1911 or so, in mercury and then lead, and all of them become superconducting, but only below liquid helium temperature. A big breakthrough was these oxide superconductors. Again, copper comes into play. These are copper oxides. Yeah, this was then above liquid nitrogen temperature, and there is a continuous search whether this could potentially reach room temperature. This is currently a very controversial field because there are properties which change with temperature, which actually destroy superconductivity. But what inspired me, or what I found interesting, was in the question about natural occurring superconductors. And indeed, there's a very unusual mineral which was discovered not too long ago. And this is this rhenium sulfide compound. Now, these are very small crystals. This is actually just the small mineral inclusion, I think, in quartz. And it has a very unusual structure. So you have these sulfur atoms, and then you form these cages of these rhenium atoms. And indeed, this was came from, I think it was discovered in the Ural. and was indeed shown to be a natural superconductor. This was on a synthetic compound to have adequate purity. And it's a fairly low temperature phase transition, but here's how the resistance looks like. And so you got sort of a normal behavior. You're cooling it. The resistance goes down gradually. And then suddenly at low temperatures, assuming at a few Kelvin temperature, the resistivity disappears, so it becomes a superconductor. Now, there's a mineral, though, you can find in Colorado, which shows the same behavior. This was actually discovered much earlier. And this is cobalt. Cobalt is actually a copper ore. It forms nice iridescent crystals. And you would think, actually, this can't be a very complicated lattice structure if you just have one copper and one sulfur atom per unit cell. But it actually turns out, and this is, again, a theme you've seen now a few times, we have two sublattices where these copper ions sit in a different coordination. So we have this, this tetrahedral coordination, and then we have a planar coordination, and they alternate. And so we have two sublattices, and this makes it a suspect that something interesting can happen. And it actually turns out that because sulfur is actually now the complex ingredient, that we have different oxidation stages. And so this is because also the sulfur can pair and then have a negative charge. And so we have copper 1+, and then we have copper 2+ on these different lattice sites. And this actually becomes a superconductor, and this was already noticed by Meissner, after whom the Meissner effect and the magnetic field phenomena was described, and it has a transition temperature also fairly low, but these are the original measurements from 1929, and these are heroic experiments at that time with that limited technology available to actually make such measurements. And so here you see that, that sharp decrease, and there is a residual conductance. This is because of the lack of purity and the general difficulty of these measurements, but it is indeed become superconducting as described in this work in 1929. So there are other materials, and then I think we'll conclude it and we'll take some questions, which you may wonder about whether if I take something much simpler, I don't want to have multiple different oxidation stages and sublattices and different elements which I'm all mixing together. What if I just take my diamond necklace and see if I can get a quantum property out of that? Or I take the more gemstone version of that ugly form of cubic carbon and this layered graphite. Okay, I'm joking, right? So that's often described the other way, right? But it actually turns out that your diamond necklace is actually not as exciting as the ugly version of graphite. Yeah, these are the two main different phases of carbon. One is where you have this hexagonal honeycomb pattern of the carbon arrangement, and then in diamond you have a three-dimensional arrangement. But what's fascinating now that this extremely simple structure of graphite in the single layer form, it's called graphene, and that actually allows you to generate quantum phenomena by something very unusual. And this is now when you take just two sheets of this graphene, and then you rotate this crystallographic orientation normal to that surface, you form, again, a beautiful pattern. So this whole talk is about beautiful pattern, which is a moire pattern. Yeah? And so depending on this rotation angle, you get this superstructure with different degree of periodicity. And this is this moire structure, which is also widely known in art. Yeah? And when you do this, you change something different than what we discussed so far. It's mesmerizing, isn't it? And nobody's paying attention to me anymore. I see this. Everybody's already hypnotized here, right? That initially we spoke about the individual lattice structure where the relative atom arrangement and neighboring atoms matter. But now what happens is that you get this supercell, and the supercell behavior changes the electronic configuration in a qualitatively new way. Where this actually then itself allows the generation of new quantum states. And this has become an extremely rich laboratory, simply two sheets of carbon on top of each other with the right twist angle. You put electrodes on and you cool it, and then at a particular so-called magic angle, if you twist it 1.1 degree, then you form the right periodicity of the supercell in relation to the individual unit cell of graphene. And then at very low temperature, you actually get a superconducting phase. Yeah? And so this is actually, again, inspirational that even the simplest material actually gives you such unusual quantum phenomena. And this has now shifted the field. Let me get you back to the bigger picture of mineralogy, where now new mineral discoveries are not so much looked at anymore as, oh, here's just another mineral, and it's been sort of this field initially, historically, from this very descriptive form, which now only in the very recent years has actually been where a lot of new mineral discoveries were immediately looked at. Do we have interesting structural motifs? And would they inspire then the design of new quantum phases? And here's a very recent mineral described in 2023, which is what's called a sulfur salt. It has sulfur and tellurium, and then there's antimony and bismuth. And it turns out that this forms these sheets, these tellurium sheets, which have this zigzag pattern. And it actually turns out that this such a sheet of this distorted square net would actually suggest to be a good candidate for what's called the Dirac semi-metal. This is a material which is similar then to graphene, and that would be a potential candidate for new materials. So there is a very rich behavior, of course, with these different materials, and none of what I showed you had anything to do with light, which is actually our research. So there is another degree of freedom where we can plug in light. This is what we do in our work, where we study, among other things, this graphene and other materials. If you want to see more of what we do and what the students in the group do, you can go to that website. So let me summarize a little bit the idea that how minerals inspire material science, and conversely. So we have naturally occurring minerals, and they do inspire the design and the discovery of novel materials through interesting structural motifs and elemental compositions. And conversely, we have now discovered in nature really rare and maybe unimaginable structures, which you know only from quilting, but not that this is actually a naturally possible structure. And these new structural motifs can then be theoretically analyzed and can form a predictive material science future. And then conversely, for the earth scientists in the room, that from these synthetic conditions under which then some of these materials could be made, this would then reinform in earth science where mineral forming conditions would either allow to explain properties for ore forming in petrographic and petrological processes, but then conversely also were then the natural conditions under earth, conditions of temperature and pressure and certain hydrothermal conditions would inspire then also new synthetic conditions. And this is sort of a list of materials of various degree of technological maturity for applications from semiconductors and new forms of semiconductors for computing data storage. We have a lot of forms of exotic magnetism also for data storage. And then there's thermoelectric materials, and then what we don't know yet, whether some of these more quantum spin liquid or topological materials would actually provide the basis for some future technology. So with that, I'd like to thank you for your attention, and I'm happy to take questions. Yeah, microphone is better. Then I can actually hear the question.
Well, I've got one. So this is had me think about what engineers are often doing is biomimicry. They try to create new devices based on things that nature has solved the problem for in animals and plants. And you're sort of looking at geomimicry. How do you use things that happen in nature, right, to be able to get ideas to form new types of materials that are technologically interesting?
Right. That was a comment or a question?
Well, you can elaborate on that.
So, well, okay, I can elaborate. So yes, so a lot of biological structures, of course, is inspiring for technology. You know, whether it's flight, right, and photosynthesis for photovoltaics, right? How nature or living matter converts sunlight to energy, or the biomechanics, right, and friction on the shark skin. You know, these are all exciting topics. These are primarily, I would say, classical effects, yeah, which in a good way are easier to describe and understand, yeah, because you don't have this complex interaction of so many degrees of freedom. Some of it has to do that the chemistry of life, it happens up here, yeah. This is all carbon-based, oxygen and hydrogen. Yeah, this is what makes most of our body weight, actually, with a little bit bone structure out of calcium. Yeah? So this is a different world of this type of chemistry versus the chemistry of these transition metals. And this is why there's actually an interesting parallel, actually, where we could make a nice table of what type of physical phenomena and technologies derived from life-inspired versus the Earth-inspired form.
This way it'll get recorded.
Oh, wonderful. How does one obtain layers of graphite that are rotated at a specific angle? Do you just make lots of it and look for it, or do you build it that way?
So it is actually surprisingly easy, and again, surprisingly it took so long. You actually take a piece of graphite, and then you take an adhesive tape, yeah, and then you just pull some sheets off. And of course, multiple sheets will stick to it. Then you take this adhesive tape with some of this graphite stuck to it, and then you dip it down on a glass slide and keep pulling. And then it's sort of a force interplay between the interaction with your glass slide versus this interlayer, so-called van der Waals interaction. And then you keep pulling, and then eventually you may be left with just one crumbly sheet. Yeah? But then with appropriate microscope techniques, you can find and locate an individual sheet of that graphite. Yeah. So, okay, so that's now the other part. So what you do is you take actually a sheet down, and we don't do this because it's actually tedious. I have my grad students do intellectually more demanding things, which they don't suffer less, though. So you would take a sheet down. Now say, you know, I have a monolayer. And then you come again with your tape, and then you put it down on half of it and just rip it apart. So then you know I have these two pieces which have the same crystallographic orientation. And then you translate it over, have a rotation stage, rotate by 1.1 degree, and then try to put it down. And then you have to be lucky. This is why the tedious part comes when you pull it off, that it stays there, right? And that's why you need a lot of, those groups who do this have a lot of undergraduates in the group who tediously do this. But then they always are doing this with high motivation because they all get their name on a significant paper when they discover an exciting quantum property. Paul, there was another question behind there, actually. Was there? Yeah.
Sorry. There, here.
It was a shy question.
I understand that because this is the physics department, we do things from a physics perspective, but I understand that material science is a very interdisciplinary field, but I want to understand what the difference is in our methods and techniques from, like, for example, chemists or actual material scientists.
Yeah, okay, that's a great question, actually. So where does sort of, how should we put, where does, let me actually go back to this earlier question. Where does material science start and condensed matter physics end? And in fact, topological and complex mathematics come into play, right? So maybe this is actually a good graph. So I would say a lot on the sort of practical side, yeah, where it comes to device engineering. Yeah, that's the engineering side of material science. Then comes sort of more a basic fundamental material science, where you really worry more about, say, these, how do I combine and modify different compositions to play around in trying to get different multiferroic or superconducting phases. The condensed matter physics side starts then when we go more onto the fundamental basic questions, yeah, then often in close collaboration with theorists who then trying to solve at variable degree of success the underlying quantum mechanical equations. Yeah, that's sort of where I would say these different fall, but there is a lot of overlap and a lot of collaboration. There are certainly people in physics who work more applied, versus you find people in material science and engineering who are more fundamental than some of the applied people in physics. Yeah, so this is there's no clean boundary, and this is good this way. Yeah, and then of course chemistry is sort of the other dimension. Yeah, where it comes to pure synthetic aspect, right, in material synthesis. Yeah.
So I want to thank everyone for coming, and Markus will be happy to answer a few more questions down front, but thank you very much. And next month, it's a discussion of the history of the Schrödinger equation. So thank you.